explanation of this structure is that all the ligands, ligands means they are electron donors. Okay, as you can see, they have lone pair of electrons. So ligands are electron donors which can donate an electron pair to a central transition metal ion. Transition metal ion in this case is iron. Okay. Now the coordination number. What is the coordination number of the complex? Coordination number means how many ligands are attached to the central metal atom, which is the number of coordinate bonds to the central metal ion. In this case, it is 6. Okay. Some ligands can form 2 coordinate bonds from each ion or molecule to the transition metal ion. These are called your bidentate ligands. For example, ethylene diamine. Ethylene diamine. Okay. In ethylene diamine, it is something like this: NH2, CH2, CH2, NH2. So it can form the coordinate bond with this nitrogen also. It can form the coordinate bond with this nitrogen also. So it is known as bidentate ligands. Most ligands such as water, ammonia, for example, water, it have only one lone pair on lone pairs on oxygen. That means this side can attach to the central metal atom. Ammonia also have only the lone pair of electrons on nitrogen. That means this side can attach to the central metal atom. So these are called as monodentate ligands. Here, what are bidentate and what are monodentate ligands?
Ma'am, can you repeat again?
I'm saying that what is coordination number? Coordination number means number of coordinate bonds which are attached to the central metal atom. So this is the central metal atom here, iron. Okay, now how many bonds it is making? 1, 3, 4, 5, 6. So this is the coordination number of this complex. Coordination number is 6. Now you can see here that this is your H2O, okay, water molecule. Oxygen have 2 lone pair of electrons. Now this lone pair of electrons can form only one bond with the central metal atom. So these type of ligands are known as monodentate ligands. Okay, which have only one donor site. Monodentate means they have only one donor site. But the next thing is bidentate ligands. So in bidentate ligands, they have 2 donor sites. In bidentate ligands, like ethylene diamine is an example, it have 2 donor sites. For example, ethylene diamine is like this: CH2, CH2, NH2, NH2. So it have 2 donor sites. One is this with this nitrogen, and one is this with this nitrogen. Okay, so it form a chelate complex. Okay, the ring is formed. We'll see in the next example. First, write it down.
Yes, ma'am.
For example, these structures, you can see here we have nickel NiCN4 2 minus. Okay. Tetracyanonickel. And here we have cobalt tetrachlorocobalt. So basically these are the structures where you should know these basic terms, that Cn is the ligand and nickel is the central metal atom. What is the coordination number of this complex?
Ma'am, 4.
Yes, and for this?
4, ma'am.
Yes. So this complex ion which is formed between a transition metal ion. What is the name of transition metal ion in A part?
Nickel 2
And A
plus.
part?
Cobalt 2 plus.
Yes. So this is the complexes which are formed between the transition metal ion. Okay. And a larger ligand can only fit 4, not 6 ligands around the central ion. So this we'll study in hybridization part. So these are arranged in either a square planar shape. This one is known as square planar shape because you can see it is type of square. And this where the bond angle is 109.8 degree is your tetrahedral shape. Okay, that means what? That means coordination number 4. It may be square planar, it may be tetrahedral, and that we'll study in the chemical bonding. Okay.
Yes, ma'am.
It is 109.5 degree. This is the tetrahedral angle. After doing this, tell me the oxidation number of nickel here and oxidation number of cobalt here.
Ma'am, is the oxidation number for both +2?
The easy method to calculate the oxidation number for nickel, it is X, we don't know. For cyanide, oxidation number is 1. So it is 4 cyanide, it is -4 -2. So X is equal to -2 plus 4, then X comes out to be plus. Similarly in this case. Now this, what I'm telling you about the bidentate ligand, it's highly diamine, that is NH2CH2CH2NH2. So you can see here you have two donor sites. One donor site is this and one donor site is this. So it makes a ringed complex. It is making a ringed, or you can say chelate complex. Okay, because it is closing, this is your one ligand, this hole is your one ligand and it is closing it. Okay, so it is forming a ring structure. How many ligands are used in this? Can you tell me after looking at the structure?
Ma'am, 6?
No, this is one ligand. This entire is one ligand. 1, 2, 3. So the ligands which are involved here are 3. So ethylene diamine, instead of writing all the big word, we can write it En. En means ethylene diamine. So this becomes cobalt En3 2+. Okay, so this is also a complex ion. It contains bidentate ligand. Okay, so the short form of writing this ligand is En. Okay, another example of bidentate ligand is C2O4 2-. This is another example. This is known as oxalate ion. Okay, oxalate, and you can write in short form OX. Okay, oxalate is what? COO minus, CO minus. Okay, this is your oxalate ion. So here you have this donor side, oxygen side, and this also oxygen have lone pairs. So here also you have two donor sides. That is why it is called as bidentate ligand. So you should know the name of at least these two bidentate ligands: ethylene diamine and oxalate ion. Okay, so very carefully draw this diagram. Let me clear this.
Ma'am,
Yes.
the ethane dioide ion, it is C2O42.
In which ion?
The ethanoid dioide ion.
It is written C2O4 2-. The exact structure is this. This is a typing error, otherwise these numbers are in the subscript. Okay, so I hope you can understand this.
Ma'am, for the exam, they will only ask us these compounds, right? They won't tell us to draw.
Yes, they will ask you to draw these also. So you should know how to draw them. It is very easy. You just have to make the central metal atom. Okay, coordination number, it should be given to you. Okay, then you just have to make a linked complex. So you should know the structure of, only these two are important in bidentate ligand. One is oxalate and one is ethylene ion.
Yes, ma'am.
And
Yes.
so see this. This table is very important. Here, this is your water. Okay, I am telling you all the ligands which are important. Formula of water, you know. Example, coordination number, you know, it is 6. Shape of the complex is octahedral. Similarly, ammonia. Okay, so remember that coordination number 6 here in your syllabus, it is octahedral. 6 octahedral, 6 octahedral. Okay, like this. Ammonia, you know, chloride ion you can make. Cyanide is Cn minus. Hydroxide ion is OH minus. Thiocyanate is important. It is SCN minus. Thio means sulfur. So it is SCN minus. Okay. Ethane dioate ion, which is abbreviated to OX. That means the other name for oxalate ion is ethane dioate. Okay, why it is ethane dioate? Because there are two carbon atoms. Okay, and in both these carbon atoms, your ester is forming basically. So it is ethane dioate. When you make a link complex, ester forms. 1,2-diaminoethane, it is En. So this both are important, which I have already example. Okay, so these are the structures. This is written like this. So it is 3 always. it cannot be cobalt En6. This is wrong. Okay, because cobalt does not have this much space to encounter these 6 En ligands. Because it is bidentate. It can form maximum coordination number 2. Okay. Do you want to write this down?
Yes, ma'am.
Hey students! Interested in boosting your studies? Enroll now at Keddy Edtech. We offer online tuition for the Cambridge curriculum, grades 6 to IGCSE, AS, and A-level. Start learning with us today.
Yes, ma'am.
Okay, that you have to state the oxidation number of the transition metal in all these complexes, and you have to give the formula for complex which is formed between nickel 2 plus and EDTA 4 minus. It is ethylene diamine tetraacetic acid. So this is your homework. You have to explore. It is a hexadentate ligand. Ethylene diamine tetraacetic acid.
Ma'am, give a formula for complex form means like A we should write.
Pardon?
Like what do they mean in B part?
You have to give the formula of a complex formed between nickel 2 plus and EDTA 4 minus. Tell me what should be the answer. Nickel can form the maximum coordination number of 6. It is a hexadentate ligand. Then what should be the answer?
Octahedron? Octahedron?
No, formula like this. This is the formula. So tell me what should be the formula.
Ni? NiEDTA?
How many?
3?
Think and again tell me. Think about this.
Six?
It is a hexadentate ligand.
6?
If you write 6 here, then the coordination number will become how much?
6.
No, it is a hexadentate means there are 6 donor atoms. So if you attach 1 EDTA, so there are 6 donor atoms. If you attach 6 EDTA, it will become 36 donor atoms. It is very unstable. It is not possible. I am telling maximum coordination number is 6.
2, ma'am? 2?
If you are saying 2, then 1 EDTA, it means 6 donor atoms. 2 EDTA, it means 2 donor atoms. Sorry, 2 into 6, 12 donor atoms. This is also not possible. Maximum coordination number is 6.
1, ma'am.
Yes, 1 only. The formula is nickel EDTA. Now tell me what should be the charge on this complex.
2 minus.
ED. Yes. Minus. This is the formula of the complex. Thus B part. Clear?
Ma'am, can you repeat this part again? How do you find?
I am telling that EDTA is a hexadentate ligand. Okay. You should know the meaning of monodentate. Let me write here. Monodentate. It means one donor site or one donor atom. Bidentate. Two donor atoms. 2 donor sites. Hexadentate, 6 donor sites.
Ma'am, how do you know it's hexadentate?
It is 4 nitrogen and 2 oxygen. In the next slide, I will tell you the structure of EDTA, okay, so that you can easily know that how it is 6. So I'm telling that it is, I think 2 nitrogen and 4 oxygen. Yes, it is 2 nitrogen and 4 oxygen. So it is 6 donor sites. So how do I find it? As I am telling that coordination number we have studied maximum, it is 6. Either it is 6 or it is 4. So it should be only one EDTA complex, okay? Because one EDTA means 6 donor atoms. Clear?
Yes, ma'am.
Let me tell you the structure of EDTA. EDTA means ethylene. You can easily make it ethylene, make ethylene molecule, then make diamine, then make tetraacetic acid. You can also make it tetraacetic acid. Okay, so ethylene, that means 2 carbon atoms are there. Ethylene, that means alkene is there. Okay, diamine, that means it is connected to diamine, 2 amine group, nitrogen. Tetraacetic acid, that means 1, 2, 3, 4. At these 4 positions, we have acetic acid, which is CH2COOH. Okay, but we are writing minus here to show you the donor sites. H2 minus, minus. How many oxygen sites are there? 4 oxygen sites are there, which can coordinate with the central metal atom. And how many nitrogen sites are there? Nitrogen sites are 1, and it have home pair. It can coordinate with. Clear?
Yes, ma'am.
Right?
Yes, ma'am.
Done?
Yes, ma'am.
This will study about the stereoisomerism in transition metal complexes. Okay. Can you tell me what are isomers?
They have the same molecular formula but different structural formulas.
They're not audible.
They have the same molecular formula but different structural formula.
Yes. Stereoisomerism. One is structural and one is optical. One is structural and one is stereo. So in coordination metal complexes, we study the stereoisomerism. So there are 2 types of stereoisomerism. One is geometrical and one is optical. It is very easy. Geometrical means cis-trans isomerism. Okay. Presence of a double bond in 1,2-dibromoethane means that the 2 geometrical isomers are possible. Okay. In geometrical isomerism, the essential condition is that there should be an alkene which is present. It is also present in transition metal complexes where no double bond exists. So this is a new thing which we have studied. So in this case, geometric isomerism refers to complexes with same molecular formula, but they have different geometrical arrangement of their atoms. Example you will see for the square planar complexes whose general formula is Ma2B2. M is your central metal atom, A is one type of ligand, and B is another type of ligand. Here it is written. Cis and trans platin, they are geometric isomers. In cisplatin, the chlorine atoms, they are next to each other in the square planar complex, but in trans platin, they are diagonally opposite. Okay, so in cisplatin structure, which is PT, Cl2, NH3. Okay, so this is the formula of cisplatin. So here you can see in the square planar complex, it is cis because platinum is attached to the same group at one side. But here platinum it is attached to different groups at one side, so it is transplatin. So this is the geometrical isomers. So geometrical isomers are also possible in compounds which have no double bond. We have seen that if I am writing like this, chlorine HBr, we see that it is cis isomer because it is connected with same. But if I write CCl, Cl, HBr, then it is your trans because it is opposite side where alkene is present. But in this coordination complexes, transition metal compounds. We are studying this. Why we are studying coordination chemistry? Because of this platinum. It is a transition element. Okay, so we are seeing the properties of it. So write down. Second, it has been used as an anti-cancer drug. It acts by binding to sections of the DNA in your cancer cells. It prevents cell division. But transplatin, it does not have the same beneficial medical effect. It is important that cisplatin, it has a very important biological role. It has been used as anti-cancer drug. How? It acts by binding to sections of DNA in the cancer cell, so it prevents the cell division. But transplatin, it does not have the same beneficial medical function.